Thank you, Svetlana. Welcome, everybody. Welcome to the meeting. Welcome. I am going to start by making a couple of announcements. I'll stay close to this laptop here. And to get the meeting started, I will introduce Charlotte Newell. And she's the new networking and socials lead at AIAA Houston. And she worked for Collins Aerospace and Intuitive Machines. She's now working as a mechanical engineer at Eon Innovations while she's finishing her bachelor's degree at Embry-Riddle. So please welcome Charlotte.
Hello, I'm Charlotte Newell. I want to start by saying thank you to everybody online and here in person joining us today. I want to take a moment to introduce AIAA Houston. So AIAA Houston, which stands for the American Institute of Aeronautics and Astronautics, is a group of people passionate about aviation and aerospace. We have students, engineers, scientists, educators, and professionals from all different parts of the industry coming together to discuss and share our passions. Our goal is to create an opportunity for people in the community to come together to connect, learn, and share their experiences. We do this through our happy hours, lunch and learns, and many other activities. Today, I have the privilege of telling you a little bit about Wes Kelly before we start this amazing lecture about orbital mechanics. Wes Kelly, after Air Force service in Europe with a flying unit, attended the University of Michigan and University of Washington, Seattle. He obtained his bachelor's and master's degree in aerospace engineering, doing additional studies in astrophysics. During his engineering career, a significant portion was in the development of human spaceflight with the space shuttle in the 1970s and later the ISS in the 1990s, as well as a number of payloads and launch systems work. As an entrepreneur, Mr. Kelly and his colleagues founded Triton Systems LLC. They developed a partially reusable launch system, and the concept was submitted to the ISS resupply competition and later addressed towards small satellite launch. Recently, he's worked as an adjunct in the University of Houston, Clear Lake, teaching astronomy and electives such as exoplanets and orbital mechanics, topics related to today's talk. To introduce today's subject, please welcome Dr. Shagan Thomas.
Thank you very much. I'm not going to take too much of your time since we like to give most of the time to Wes here. I knew Wes, I've known him now for what, 20, 30 years. And one thing I can say about him is he's a very brilliant and very determined engineer. So he's worked on a lot of projects. And what I'm going to try to walk you through is some of the projects he worked on and how we actually got to where we are today. She mentioned some of the space station and space shuttle work, but what Wes excelled in is working some of the advanced concepts like LFBB, liquid flight back booster. What that name tells you is that we're going to turn the solids into liquid boosters and also be able to fly them back to the Cape after launch. We worked on some projects like the spaceport in Idaho. You can imagine why we want to put a spaceport in Idaho. So he's laughing because of what we found out launching some of those vehicles and where some of the stages drop, like in Chicago, like in Ontario, well, going into orbit. But we were able to successfully come up with a workable solution based on a lot of the work he did. Prior to that, a lot of people don't fully realize that he actually worked with the Air Force. He logged about 1,400 hours doing reconnaissance work. I'm glad he didn't get shot down, but he's here with us today. I brought a few of the things that I was going to talk about here, just in the interest of time. If you want to see some of those, I have copies that I can hand out to you. But in the meantime, I'll turn the podium over to Wes to come and talk about what we have today.
I want to thank Shagan for a wonderful introduction. It was a pleasure to work with Shagan over the years and our colleagues at Lockheed and the subsequent organizations. Now and then we just change the sign. Well, I guess I'm here. I guess it's kind of a shock. I'll just see if I can advance from the title page. Of course, I'll just mention the title before I go. And that's Problems in Orbital Mechanics. And by the way, can you hear me all right?
Yes.
Yes.
Oh, okay, fine. And why we have them. And addressing the particular problem of time of flight. And time of flight, as a definition in orbital mechanics, is having eccentricity and two angular positions and being able to solve that as a problem. And it wasn't always around, so it's kind of a detective story. How did we get to that point? Now, I used this chart as a publicity piece, like as a flyer, because if you look at it, and is there a ostensibly there's symmetry here. There are 2 points on Mars's orbit that these paths from Earth are reaching. One is at 270 degrees, the other is at 90 degrees. And I'll talk about that a little bit more later. But there's a symmetry of here's a perihelion Mars, and here's the exohelion. It's eccentric. But if you look closely at it, there's some differences in that. And it's kind of a question, do we ignore those? Or do we try to exploit them? Is it just a big mistake? And that's what kind of what I sort of ran into as I was doing this analysis. Is there something real there? So I'd like to just say a few words in memory of a couple of our colleagues. One is local, had been working here. I used to run into him now and then at the Starbucks on NASA Road 1. At the time I was working on a different problem, I guess, wings. And he was working on upgrading Copernicus. But it did some wonderful work on that. It's used throughout the industry and here at NASA. And I wish I had an opportunity to tell him about what I was doing on this, because I'm sure he would make it better. It's a different philosophy, but all the same, I think there's some complementarity in there. And here's another gentleman. It figures it kind of ties into the story, beginning and the end. I didn't want to talk, just drone about orbital mechanics, but have some human elements in this story too, and which I'll probably wrap up with about our adventures in 1972. That's pretty much what we saw on our class trip. I was taking orbital mechanics with Professor Buning back then, and at that time he had scored some tickets for our orbital mechanics class. The previous flight, I guess it was Apollo 15, were all Michigan graduates, and they were there at homecoming day. And then, of course, I think he taught a number of them as well. And by hook or crook, he had tickets to get us as close as that to watch the flight. And it was quite a journey down. It took about 24 hours to get there and 24 hours to get back. And in between, there was the biggest traffic jam I ever saw in my life. Not at the moon, of course, but saying goodbye to the astronauts that were on their way. But in this case, I think we're going to focus mostly on Mars. I will go back to reflect on the lunar experience now and then. And a little bit faded on there. It might be a little bit overhead lighting. It's just, can we darken a little bit perhaps? Oh, good. I don't know if that's going to be a recurring problem, but I think that Mars might look a little bit better with the light turned down a little bit. How's that? Oh, okay. And in the corner, you can see kind of the schematic of two representations of Earth and Mars. In this case, on the right, it's circular orbits. But in fact, if you're headed to Mars and going at a particular time, in your position in the earthly orbit, you arrive 180 degrees later at some eccentric position in Mars's orbit between its closest point to the Earth, to the sun and its farthest. And that's a significant problem for space travelers, depending on when you're going to go and how you're going to get there, or what conditions are going to be in flight. And we've got a lot of expectations about Mars, of course. I've read a lot of science fiction from from day one, or I learned to read, I guess. And Mars, as it appears now to us, had kind of a colorful past, probably with a lot of oceanic coverage. And we have kind of a wishful future about it, like, well, we'll have some dams and streams someday. And it's becoming a place. The Jezero crater, I guess, where we're getting a whole lot of mapping activity. We have a lander there and collecting samples for return. See if I can give you a kind of a trace of its path. You can see it where it came down. You can see it going down. Mars, the point is, Mars is becoming a place. It's a faraway place, an adventurous place, and you have a growing expectation that somehow we can reach there, get there, and explore it further. It's tantalizing, I guess. I remember a film back in, I was a kid, it was called The Wheeler Dealers. And I don't remember much of the plot, it was rather complicated. But I guess at one point, James Gardner and friends stop off in an English or New England town, and they're asking for directions. And the most memorable line of the whole film was, "What? You can't get there from here." And that's sometimes how we might get the feeling that here we are on Earth, and we just can't get there from here because of a number of reasons. So this presentation doesn't solve all the problems, but I think it makes just a little bit of progress. I have reservations about, where to put this in the presentation, but I think it's kind of key, and that's about the education of people that work on orbital mechanics. And I looked at all the books that I'd been reading about it, and I saw something that wasn't possible to see until in recent years. I don't think that any of these textbooks addressed it until about just a couple of exceptions. I see three there that are circled here. Yes. And that is about what the ostensible subject of this presentation is time of flight. I mean, what is time of flight? Well, it takes a certain amount of time to get from here to there, but can you do anything with it analytically? And that's the important thing. You can get analytical solutions for the time of flight. Whereas most of these textbooks do not provide an analytical solution. They encourage or say, well, it's the only recourse you have is to iterate. Start with a guess and then try to converge on what the answer is. There's even that illustration in the Martian, where one of the heroes of the story is working under a bridge on a computer, trying to figure out a way to get back to Mars to rescue the astronaut that's marooned there. But it really doesn't necessarily have to be like that, and especially not in the future. To give kind of an indication, some of the earliest textbooks you might come across I'll say in a college course is one by an American astronomer, very accomplished, but very mathematical. And his name is Forrest Moulton. I think he worked in Chicago. And he put out a textbook in 1920 and it's still in paperback at Dover. And it's got loads of calculation, but there's no acknowledgement anywhere in there as such a thing as calculating the time of flight. If you got two angles and you know the eccentricity, it's unknown to them. This second one, it's buried in there, but it isn't explained very well. I think it was a 3-volume book, and maybe volume 3 explains it better. But every once in a while I come across it and use it, and I didn't know why it worked. And then there's a book that I gave to our colleagues who were working with us on space station, the Russians that who were visiting. Figured they'd give them a going away present. It's a paperback by a gentleman named Thompson. And he had just made mention of the time of flight calculations and how he solved the problem. And he said he did it with a CRC integral. And the CRC integral, tables of calculus problems, what their solutions were. It was published in 1930, so it was after Moulton. But then it sort of went nowhere. He didn't do anything with it, really. And then we have a succession of people that use quite frequently for, trying to solve problems and get over my head, and they have nothing about time of flight. Richard Batten had this book back in 1960s, very pioneering. He went on to had guidance for Apollo. So he was a very knowledgeable man in the area, but it's missing in his book. There's no provision for figuring out if you're here on this particular orbit and you want to get to there, how long is it going to take? And the same thing is true for a succession of other people. The paperback that's probably used by a number of people, possibly in here, is Bate, Bueller, and White at the Air Force Academy. Same thing. Celestial mechanics people, they always do the same thing as well. And then recently, I think in 1997, there was a complete derivation of how it was related to another quantity called eccentric anomaly. So I guess I'm kind of laying out everything I'm going to talk about on this one chart. And that's the problem with this. And then finally, I think in the case of this last one, it was 2021, the whole shebang is laid out where you can use it. So what else can I say about this before I go on to the rest of the material? I think what it is, why this doesn't appear, is the traditions of astronomy. Astronomy in the early 19th century, it was about finding an asteroid. Say, oh, I see an asteroid, but it's going to go behind the sun. Where's it going to be when it comes out? So you get a couple of readings on where it is, positions, when the sky is right, and you can see where it is, and then you can do a calculation, then you iterate on it and try to converge to a solution. And that's where astronomy was in the 19th century. It kept on doing that, even up to the time of Moulton. And then there's been a transition, but not complete, because the Air Force, for a lot of its missions, is really concerned about, well, there's something up in the sky orbiting the Earth. We just got a fix on it. Where is it going to go? We hadn't seen it before. Is it going to crash on United States territory? So consequently, a whole lot of books that we use in the field, such as the trio of Air Force Academy specialists, they teach people how to track things, but they don't teach people how to design rockets and spacecraft. How much fuel do you need? How big a vehicle do you can build? How much payload you can deliver under certain circumstances? So that's really what I'm here to talk about, because this is still not widely known. So, see if I remember what this one is about. What was done here in this report, I guess the background of these charts, is looked at going to Mars. And we just sort of pounded away at Mars, how you get there, and when you're going to get there, where you're going to get there, perihelion or aphelion, or the right or left side of aphelion, and how much energy it's going to take, and then what can you do about it? Can you improve on the calculations? And there are a couple of ways you can do that. Well, for one thing, there is sensitivity to what kind of vehicle you use, what type of propellant. There's several that are used a lot in rocket applications. Hydrogen, methane, kerosene with liquid oxygen. And then there is the nuclear thermal. I think there was a recent article about somebody's new idea for new configuration for a nuclear thermal vehicle. And the higher the specific impulse is, the more bang you get from burning the pound of propellant. And as the numbers go higher, you can have more payload generally, or else trade it with hardware of another sort. Would not be hit as hard by, well, the weight of the vehicle itself. And there are other measures like what part of the vehicle is propellant and what part is the structure that carries the propellant. So I guess we got to the time of flight and context. Of course, I guess I am in a way sharing a lot of what should be notes. But there are a number of technologies out there, and at one point I was working on one with one of my colleagues at Lockheed. We had, well, I guess his problem was that he was looking at advanced propulsion. And there are several candidates that he was looking at that had nothing to do with the rocket equation, at least so directly, at least in terms of chemical fuel, but there were advanced programs where you might be using nuclear power for solar electric arrays, lots of solar panels, and then generating enough electricity to power a spacecraft to Mars and get it there in reduced time. An underlying reason for this is that the longer individuals were exposed to flight between Earth and Mars, the more medical risk there was due to flare-ups of the sun, background radiation from, beyond the solar system, and just being weightless for a long time. The physical fatigue of that, or else the stores try to keep a cycle going. So there are reasons to try to get to Mars faster. But in light of the discovery of this idea of time of flight, I guess I was able to solve part of this problem there to look at how long was available, based on how long it was available to get to Mars. Say if they want to get there in 60 days or 90 days, they had a configuration. Would they have enough time for the vehicle to apply the amount of thrust or impulse to change the orbit to get there? And some of them were disqualified on that basis. But another one was lurking in the background is if you get these advanced propulsion systems, this is a very expensive undertaking. You have nuclear reactors or nuclear fusion reactors out in orbit, you have radiators, you have shielding. This would be very expensive. So my point is not that these are bad ideas, but what we have now, with just slight adjustments to the orbit, you get a lot of bang for your buck without large-scale research and development programs. Well, in modeling this, the eccentricity of Mars is about 10 times that of the Earth. It's about 0.09. We'll show in the diagram what that means later. And we're about 0.01. So most of these calculations are based on just assuming a circular orbit. Otherwise, I wouldn't have had very much information to give you at all. And there's another issue here that's in the background too, as well. When do you launch to Mars and what difference does it make? Since Mars is in an eccentric orbit and we overtake Mars by having a ratio of getting there, going around the sun in about 60% of what the time it takes for Mars, we keep on overtaking Mars at a different position in its eccentric anomaly. So it's not always at a given distance from the sun when we have an opportunity to go there. And then when there's an opportunity from, say, roughly every 2 years or so, the payload that you could get there with a fixed configuration or the trajectory you might want to go is going to change the payload opportunity. Now, it's an open secret, as shall we say, that the Johnson Space Center looks at what is going to be done on the surface of Mars if the astronauts get there. You're going to have a big party. You're going to have pressurized facilities for people to live and golf carts to look around. But there's still a problem with how you're going to get all that in one individual year. And if you have a spacecraft of a general design, there are going to be good years and bad years for the delivery. So what I've got here is just, you don't have to memorize this or anything, but just based on having a circular orbit of Mars and the Earth, there would be a basis for, and this would be the first case here, 0. There'd be variations in how much payload we could get there. And whether it's in terms of tons or delta V in velocity, from one opportunity to the next. So inherent in this is that from one launch window to another, conditions are going to be favoring more payload or less payload, and that might have some effect on decisions like, well, are we able to ship a bulldozer to Mars at this launch window with this particular rocket or not, or what do we have to offload, as the case might be. And consequently, you could get some values for those variations. For various types of propulsion here, we have liquid methane, which is, of course, we're hearing a lot about these days because we've got hardware about 100 metric ton payload delivery into orbit. And liquid hydrogen, I guess, kind of a tradition with the shuttle and its variants. And then earlier that should be the nuclear would be over there, but this would be kerosene systems and how they would change in their payload capabilities. And it just documenting the case for, say, well, you have to do some planning for each year that the window opens, and then make decisions about what can be carried and how you're going to do it. So shifting the emphasis a little bit here, just so you could see Mars as a target in various contexts. Mars has a particular orientation in its principal axes in the celestial sphere that is determined right ascension. And then right ascension is not necessarily exactly where we want it either. The right ascension point, if we have it over here, is 0. So we say due east in geographical terms. We would have Mars aphelion over here. And we have an intersection point if we're going to that target over here, if we had a more energetic orbit that crossed Mars orbit, but was launched at this point. So what's the significance of that? We'll tell you later. Now, in the case of the Earth, the actual point where our perihelion is in January. That's funny. It seems pretty hot right now, but we're in the, I guess, the upper hemisphere, kind of nodding toward the sun. So that's probably more of an influence on that than anything else. And see if I can locate when we arrive at, here we are, 3rd of January. That's the, we're roughly our perihelion. I got it backward. That would be our perihelion is January, that's right. And it is around the 3rd. And it's in right ascension terms, it's 102 degrees. So it's over here. And it's conversions that are necessary if you're going from one planet to another, but in practical terms, I guess it doesn't put you much further along day-to-day life on Earth. And then just if it's a little hard to make out the difference between Mars aphelion and perihelion, this perihelion, that's aphelion, that's what they look like when they're extracted out of the diagram. This is a conceptual Mars spacecraft. I don't know how much, how long that this configuration will be supported, or if it's just a kind of concept, or what the case might be, but it's illustrated. There's propellant tanks, presumably. I would suspect that it's either for liquid methane and liquid oxygen. And then it looks like Orion spacecraft variants to go land on Mars. But there are a lot of details that are still out there. what it might look like. And then when it gets to Mars, there are issues like, well, is it going to do aero braking, or is it going to use propulsive means to park itself around Mars? And if it does either one or the other, how does that affect the payload? Well, I don't have an answer for that. Matter of fact, with the trajectories I've done, I've stopped short of getting people to Mars, you know, so they can hit it as a target. But there's still that issue of how you're going to take care of things when you get there. You're going to try to use the atmosphere to brake. And then what kind of device do you need to get that braking? And are there some trajectories that come in so hard that, well, maybe we just can't do that with the technology and still have a payload? So that's for later discussion, I suppose. But this does indicate that there is a trade buried in this between time of flight and payload delivery. And time of flight gives you possibility to consider things like, well, if I'm doing just hardware, I don't care how long it takes. Nobody's trying to get grow things in algae vats in flight, so it could take as long as necessary. But if you got human beings living in a closed environment, you might want to speed some things up somehow. And that's where we get into the technical part of this discussion. There's a solution where you can change in an orderly manner your trajectory to Mars and know where you come out. And the simple way to do it is go start out at perihelion in terms of the Earth's orbit around the sun and add velocity to it. Now you can start these do these burns in Earth orbit, but when you come out of Earth's gravitational field, you still have to take all of this into account. You want to be at a perihelion, and I'll get to those details a little bit later. But you can adjust your orbit considerably, and you can adjust the time of flight, this bottom line, by how much velocity you add, whether it's 10 feet per second, 10 meters per second, whatever the case might be. All the other parameters that are related to the time of flight and what the orbit is going to be shaped like are in there. And there's going to be a shift in the true anomaly that you intersect with Mars. Now that doesn't look obvious right now, but in the next diagram or two, you see something about the true anomaly change there, that delta F, that we can take advantage of too. Now, if you weren't trying to change the time of flight from the 180-degree transfer, where you just don't waste any extra velocity to get there, take the time it takes to do that transfer, you can solve the problem of where you're going to arrive with the formula for the radius in terms of an orbit. And it's or shall we say a conic. And the conic equation in this case would be expressed in terms of the semi-major axis of the planet or the orbit, and the true anomaly angle involved, and the eccentricity of the orbit. So if you have a 180-degree transfer or going from Earth to Mars, you put in that transfer orbit position of 180 degrees, and if you have a particular target, such as 90 degrees, 180 degrees, 35 degrees, a true anomaly, that would be the other part of this. So that would shift, this left side, would shift that transfer trajectory, the purple one, around in the orbit of Mars. And when you rearrange that, the solution is largely dependent on what's happening with this corresponding parameter P, which is actually over here. This is P, the parameter P at 90 degrees or 270 degrees. It's made up of these two elements, the semi-major axis and the eccentricity, and the same for the transfer, but the transfer is the one that's changing. So if you rearrange everything, you get the two parameters on one side and then an angle on the other. Getting lost myself. I mentioned this is a true anomaly, and then you're changing it by delta F. Now let's stop to think about it for a minute. What does that delta F mean? Is it talking about just the Mars, or is it talking about the trajectory going from Earth? Belongs to both of them. So if you change the intercept angle, you change the delta F for both the transfer trajectory and the Mars position. And that's valuable. So you can put it in both of these expressions. And then I guess you want to solve for that, the delta F, get it on a side by itself, as my algebra teacher used to always say. Take a breather here. I don't think I can do much more analysis on my feet, in one fell swoop. But just for a little background, I've got a few numerical values that are involved in this. And why are they taken out to 8 or 9 digits? Not because I know them myself, but if you're actually doing the calculations, it certainly helps take them out as far as you can and have them all consistency. And then when you start doing the calculations, you say, oh, wait, did I put the right value in there? And you can go back and check. Now and then you have to have the gravitational constant of the Earth, for example, and then other times you need the gravitational constant of the Sun. And let's see, that would be Earth's, yes, that would be Earth's eccentricity. And Mars is about 9 times that. Or the magnitude larger. And then, of course, you put this all in spreadsheets and forget about the exact numbers you actually put in there. Now, here's some more. These are more related to what Mars orbit looks like. And if you don't have these, out to these values, well, of course, the answers you get, they may not necessarily be right to begin with, but they're going to be more wrong than they were before, shall we say, or less accurate. And then it's always good to keep in mind that this angular momentum, h, and h squared divided by mu actually is p. They all these values add up to the same value of h. Angular momentum is constant. And then you can see there the ratio between how long it takes to overtake Mars in Earth's orbit, about 686 days or 687, and it's about 1.88 times as long Mars's orbit. So consequently, that's why I got to wait every 686 days to get another shot at Mars. But there is a window there. You can start early or you can start late. It's kind of like a center point, you might say. Because if it were if it was just simply one point, then a lot of these calculations wouldn't be pertinent, as you'll see. Now, another thing to think about, but it's not too consequential in this case, is that Mars does have a slightly different inclination than the Earth. It's about 1.8 degrees out of the orbital plane of the Earth, the ecliptic plane. And then there are other orbital elements listed there, the ascending node, the position of the perihelion with respect to the Earth's orbital plane. And if you're doing calculations, they'll all come up, but we won't have to go through that right now. So there's an indication of the inclination difference of Mars. It says that now and then you're just going to have to take that in account, but there is a way to do it. If I had a piece of paper, I think the easiest way to illustrate that. Going around some point, you put a crease in the paper. And that's where you do your orbital maneuver. get the line so you're headed on the orbit, the higher declination. You know, we reach a declination above the ecliptic plane, and zap Mars. But you can't do it from 180 degrees away. It won't work. You just end up at the same position you started at. Here we go. So it works out better if you do it later on rather than 100 over here. Now, there are studies that are undertaken at NASA, and I'm not privy to most of them, but I do see a pattern. I mean, when I came here in 1986, after some absence, I took a chair, an office cubicle that the previous resident had just left for Langley, Virginia. He'd been working on it in the RMS, the ARM. And then after that, he was one of the group that would publish these trajectories going to Mars. The famous ones that involve conjunction trajectories or the opposition trajectory, which I could confuse very easily when I walk out of the room and not see this picture. But the point is how much time you spend on the surface of Mars and how much time you spend getting back to Earth, and whether there's a reasonable trade in doing that. And the funny thing is I've met so many people that generate these trajectories in Virginia. And it seems like the majority have been done that way since the last 30 or 40 years, maybe longer. One of the first people I worked with at the Johnson Space Center told me about how when he was working at Langley, back in 1975, he figured out how to get the Viking 1 lander on Mars on July 4th. So most of this is imported into the Johnson Space Center, as far as I can tell. But nonetheless, there's still a reason to be able to analyze this sort of thing locally. Well, the big takeaway of those previous slides, and I'm taking the easiest example right here, is you can get that delta F on side by itself. Not always, because trigonometry gets complicated. You can do simplifications. I give a numerical value for a trigonometric expression. You can simplify it, but when you're at 90 degrees or 180 degrees, there you go. And I have to admit that of all the time I spent on this, a lot of it has just been trying to figure out how the trigonometric substitutions I've got to get if I want to go to someplace else. So I can't stand up here and say I've got something for 47 degrees and I'm completely confident that that's the answer. But I believe this methodology will get you most of the answers you want. So what is happening here is you're identifying a change in velocity, which gives you a change in aphelion. And then you get the other elements you need, and then you put them into this expression called time to flight. Now, well, it looks ugly, I agree, but the alternative is worse. It's an analytical expression. You can get values of it, and if you put it in a spreadsheet, you can calculate times of flight in orbits all day, and make another one and adapt them quickly as you like. And you could paper the walls with trajectories to Mars, and it could all be different. So many that I can't even grasp the implications. So first pass assumptions would be based on circular Earth and Mars trajectories, or orbits, shall we say. It's easier to understand how things work. The 180-degree transfer. And one thing to remember when you're drawing them is you're trying to figure out what it is going to look like. This is the important element, the semi-minor axis, and getting a calculation of that, which is up there at the top of the page. It's the largest print. V is equal to the semi-major axis times the square root of 1 minus the eccentricity squared. And then everything else should work out all right. You will need that whether you treat Mars as eccentric or as a circular orbit though, but it's the easiest to illustrate there. And of course, we might want to know about what is maybe true anomaly, because this is very essential for these calculations. It's an angle with respect to the periapsis. If you're talking about ellipses in general. And it should not be confused with the eccentric anomaly. It's quite distinct. And then, coming into this type of study, I'm a freshman or junior or senior in college, and I'm sure I couldn't keep them straight back then. Which one was eccentric anomaly, which one was true. But it's important. So what happens is when you add a little bit of velocity, and this is in terms of meters per second, you cross Mars's orbit earlier and earlier in its passage around the sun. So this F gets larger as you add meters per second. And the time of flight is measured by initially this gold angle here, a golden plot, for say the circular orbit. I think this might be, this is near the seven major axis. It's going down from about 253 days and going down further and further. Now, I have to admit that this is the most sensitive case that I found, but it's also, being that sensitive, is also quite illustrative. Makes you want to read more or find more. Now, the true anomaly intercept is going down this gray line. It starts at 180 degrees, but the period of that transfer trajectory is going up. Coincidentally, it's right around, I'll have to look at that later. So, if you're loading this expression down here, you're looking for the sine of ft or else a delta f. But the transfer to anomaly you got as this you add velocity. So it may not be ready for dress parade, but this is significant in that you have an analytical solution to an orbital mechanics problem. And as far as celestial mechanics books are concerned, you'd probably be burned as a heretic, because you don't have in celestial mechanics books time of flight as a solved problem. You have endless cases of series solutions. So this is kind of a repeat of the statement that there have been submission studies and a little bit more background on it, but especially looking at this 100 metric ton vehicle, which coincidentally or not, that's probably what the people down the south of Texas are looking at with liquid methane, but that's beyond the scope of the study. In truth, it just illustrated what can be done with chemical systems. And I mentioned something about the studies done 10 to 12 years ago, we were looking at advanced propulsion. We didn't even consider chemical propulsion at the time, other than I will climb my way out of from drowning to see that how I could calculate the trajectories by using orbital mechanics, see which ones of these high energy systems had enough time to change their orbital paths by the deadline that they were supposed to reach Mars, and some just couldn't do it at the time. But you don't have to do a whole lot of development work to get the results that I'm talking about in this study. We've already got most of the bang of the buck right now. All we need is a little guidance, which way to point things. Now we're doing on time for discussing orbital mechanics, but this is kind of the procedure involved in calculating orbits. You have a velocity at perigee, and you have an escape velocity, but in this case, we're talking about escaping from the Earth and getting on the heliocentric plane. And that has an influence on things too, what sort of economies you can have in getting into space. Because there's some nonlinear effects there. And I would call them a gain. Now, if you have a certain amount of velocity at an infinite distance from the Earth, and that arbitrarily just out of its influence, doesn't change much after, say, so many 100,000 kilometers above it, you could say that's what you're going on to the heliocentric domain with that energy. And that would be your perihelion velocity if you aim it right. But in getting up to that with an excess velocity from Earth, there's a gain involved. And the more energy you put into it, the less gain you get. Nonetheless, it's there and it can be exploited. This will have to wait for another occasion, I suspect. But looked at this in terms of increments of 0.05, kilometers a second, like 50, 100, 150 meters per second, and put it into the various orbital equations. And I think this is the part you might want to be familiar with right here. If you have an escape velocity in terms of the Earth, you would go onto a hyperbolic path, but in the orbit around the sun, you're an elliptic path if you aim it right. So you have excess velocity over escape velocity, and it might be in terms of delta V for the subscript, and then you get out on the solar plane and you add it to a circular orbit, so-called V infinity. But this is magnified by that gain that I'm talking about. And the score varies if you're aiming at the perihelion of Mars or the aphelion of Mars. The gain is more for the perihelion than it is for the aphelion. So to illustrate, right here, if you're going 1 kilometer above escape, the V infinity, or if you come on the solar stage at 1 kilometer a second, your VPOE, the part that was above escape velocity, is just about 5 meters per second, excuse me, 50 meters per second, and the gain is about 21 times that. Now for Mars, you're aiming for things that are in a higher range here. I'll show you it a little later, but the gain has to be taken into account. And the bottom line is not that you have to go through the calculations, but they can be done, and they're shown how in this particular presentation. So for the positions of the Mars, you have its perihelion, the 90-degree point, the semi-major axis value, it's around 95 degrees of true anomaly, and arbitrary positions elsewhere. And then there's the aphelion. And over here, you have how much you have to adjust your exit velocity in the Earth coordinates due to that gain versus how much you would have to do it if you applied it in orbit around the sun. So it's advantageous. I guess a lot of people might get the notion that, well, you build a base in one of the stability points going around the sun or around the Earth or else around the moon, and then build a base there and launch things to the Earth's solar system. That's advantageous. Well, maybe it is in one way or another, but in this case, you get a lot of, if you play your cards right, you can get a lot of advantages by starting at low Earth orbit and applying that extra velocity. And of course, the gain, the faster you leave, the less gain you get, is the bottom line here with the same orbital targets. Now, this diagram kind of recurs with different axes, but there are a lot of effects in orbital mechanics that seem to drop off rather quickly. I mean, you discover them saying, well, wow, if I could just exploit that linearly as it goes on, but added velocity sort of drops off in this asymptotic way, or in many cases. For instance, if a comet were to pass through the Earth's sphere of influence, it's going very fast and its path is not bent very much. But if it's going slower, it gets bent considerably. What is this mess? I got some results for the three types of propellant, I guess. But it's not something you have to carry away. It's just that most of this data has been derived from looking at targets for the Earth, from Earth to the Mars, and what the payloads can be. And for planning purposes, that would be significant if you're planning to put something on the surface of Mars, and how you allocate your resources with aerobraking or propellant to slow you down, or provisions to get right back. But as I was doing these calculations and the sensitivity for these delta V changes, I noticed that the case of the 90-degree transfer was rather sensitive, which takes us back to that first illustration. And this is what I see there. Now, if you're heading to 90 degrees true anomaly of Mars, I can't see how you can avoid crossing the orbit of Mars on your way there. And consequently, your sensitivity of time of flight, how much you can reduce your time to get there, is rather sensitive anyway, even ignoring it. I get the best results there. And
So yes, we've got about 5 minutes to 1 o'clock, so we might not have too much time for questions, but
okay, I understand.
yeah, 5 more minutes, thanks.
Okay, well, this is, at any rate, this is something worth investigating. I certainly wasn't going to throw it in the trash, say that's ridiculous. So there are a number of other cases you're looking at going around the clock, 90 degrees, where you get a steep drop off of time of flight as you're going to true anomaly 90 degrees, but it's not so deep for 270 degrees. This is some of the background of what I've been talking about. So I'll skip over that. I'll just say that there's another application for this. When I started doing this, I was kind of unpacking my things from the office and deciding what to do with a lot of material. And I was reading over Science magazine publications, and one was on exoplanet transits. And found myself looking at some material that was written on this subject. And it was taken from a depth standpoint. What you could see is determine about the planetary atmosphere. If you're looking at the depth of, due to the shadow and the extinction of the stellar source. But I started looking at the time of flight and velocity entering and exiting gave you an indication of what type of orbit the planet was in. And it's kind of like if you were using thermodynamic tables. If you were looking at compressible flow, you have features of particular solutions to time of flight. And plus you have the spherical trigonometry of the passage, whether it's at the equator or at a given latitude. And from that, you can sort of piece together what type of orbit it is besides just simply the period. So in certain cases, you could figure out what was the orbit of the extrasolar planet. Was it had a eccentricity, where was its aphelion, or I guess, or in this case for a star, periapsis and apsis in crossing the star. So there's some discussion I hope to talk about present day while we're looking at thinking about Mars. There's also a lot of concentration on the moon, and was looking at the previous exercise from the 19th century. It's fascinated by how accurate it was or wasn't, and how it came to be, and how very similar it was to Apollo 8 that just blew my mind when it occurred. Around 2005, I was looking at some trajectories myself. Occupied with we were both occupied, I guess, at that time with looking at lunar flight on the Rhine. So here's kind of a shot across the bow, but with a little practice, got a little bit better at it. And you can see where started to get the trajectories by, I guess, feedback. There's some stories I'd like to tell about what had happened there, but I think we're kind of out of time, perhaps a chapter 2 sometime. And I guess I would open up the floor to have any questions or discussion.
We'll open that up for questions and we'll turn on the lights a little bit. We scheduled this from noon to 1, but nobody else has the room. We can stay here. I'll say hello to the online audience. Hi, Svetlana, are you still there? Well, I don't hear her, but hopefully she's hearing me. I'll be texting with Svetlana. So like I say, we would like to encourage people to network. Those of us who work in this industry at the moment are always looking for an opportunity to do that. If we may, we'll get a photograph with Shogun and Charlotte and Wes and me. It's the 4 of us. So I encourage everybody to network, and even if you're one of our walk-in guests, I want to encourage you to sample the stuffed mushrooms, because there's about 4 of them left back there. They're really big. So we're going to stay here and talk. And yeah, the lights are on again, so we can stand up, walk around and network and talk, and we'll try to snap that group photo too.
Before you want to put it in things into perspective, how much time do you think you gain using this method of calculation, Earth to Mars, as opposed to what we do now?
It would, if you have a 180-degree transfer,
Keeping everything else constant.
yeah,
Yeah.
it would change the. It would be a question of you had from 50 to 200 meters per second. I've got calculations for that shown in the diagram, and that is cutting down the time by roughly 30 to 10 of days.
Tens of days.
Yes, in some cases it might be higher than that. Like at 90 degrees, it really drops considerably, even 100 days.
Okay. Quite significant. Okay.
Well, John Rangel, our section chair, AIAA Houston, would like to thank you, Wes. We're really, really happy with the turnout here, the people in the room, and 21 people online. So we are very, very relieved and exhausted, and very grateful to Wes Kelly, Triton Systems, LLC. And coming up, we're going to
We
check.
can try to see some of the questions that were online.
Oh, okay.
I appreciate the opportunity of having to discuss this.
A few months ago, Wes Kelly told us Rachel Tillman's in town with the Viking Mars.
This was last year.
Yeah, the Viking Mars Preservation Project. And she was traveling the country in her own vehicle with her 2 dogs. Her father worked on Viking Mars with NASA, the University of Washington, and she has a rover that she inherited. She's shown it at the Smithsonian. But she's gonna keep it. She's not gonna give it to the Smithsonian, and she's got a big project of preserving that. So Wes Kelly told us about that. We brought her in for a lunch and learn at Bayhab nearby. And then our close friend Al Jackson did a lunch and learn. And now we have Wes Kelly doing this one. So we're really, really grateful. Wes has been really active in that sense. Anything, any news about online?
The question is this, Jorge, which is, roughly speaking, how does plasma-based rockets compare to chemical, thermal, electrical, and nuclear? So I don't know if you wanted to kind of.
Yeah, and the laptop will be your microphone if you could answer.
Well, let's see. Plasma-based rockets, I think they were anticipating specific impulses much higher. But on the other hand, the thrust levels might be much lower, so it's kind of a question of how much impulse they can apply right away. Or in a time, if they're trying to shorten the time to get to a place, the faster they want to get there, the more difficult it is to get to the thrust to do it. So that and I think the big issue there is how much investment it might take to get to that point. It might be an improvement after you can get someplace. But to get there in the first place, I think the most direct way would be to use chemical propulsion available now.
And our friend in Oregon, Dan Elmo, answered online. He said chemical ISP less than 450 seconds. Nuclear thermal ISP equaled 900 seconds. My career was on a different vocabulary.
And then I actually have another question for you. For somebody who doesn't have a background in orbital mechanics, or somebody who maybe is a student that would be interested in learning, maybe from the very basics to something more complex, where would somebody start to get into this? I mean, I just don't even know where you would start. Tell somebody below, is there a certain book you recommend or something that you?
Well, there are a number of books that have been written on orbital mechanics, and I illustrated them there. But I think that this is kind of a community thing that we ought to be working on. We have a branch of the University of Houston, and we have a lot of people that need tools like this. And from my personal point of view, I'd be glad to teach them, but they still need a form of one sort or another. Either the university provides it or they're directed studies, where somebody comes in and gives a seminar on it. I won't name anybody, but I would love to. Yeah. Mhm. I'll see if he's available.
Did anybody else have any questions?
Well, thanks, everybody. Like I said, we're going to wander around the network. Thanks again.
Thank you. Glad to have this opportunity.
Maybe with that.
Formed a little company, Triton.
Right.
Does it go with mother?
Working with a number of other people, but we kind of pulled it off.